Wizard.
Hi, Brian.
What do you want me to take my bike for?
Well, I want you to help me do a scientific experiment that involves this ball.
Yeah.
You take the ball, ride down there, turn around, and come down here at a fairly good clip, and when you get to that stake, throw the ball up in the air and catch it.
Okay.
Can you do that? Okay.
Yep.
Okay, now I want you to describe what happened to the ball.
Okay, well, I threw the ball up at that stake and went up in the air and it came down and I caught it.
You think it went straight up?
Yeah, it went straight up and it came
In fact,
straight
you
down.
tried to throw it straight up, right?
Yeah.
Didn't go that way, though.
It didn't?
Nope. Not according to the way I'm looking at it.
Oh.
You see, when you threw the ball up, it had forward motion because you were riding along on your bike. And to me, standing here watching you, it described an arc like that.
Oh, okay.
And as a matter of fact, let's change positions now.
Okay.
Can I ride your bike?
Sure.
Okay, here you take the stake. This time, I'll throw the ball up as I ride by, and you see if you agree with me that it describes an arc.
Okay.
Are you ready?
Ready? It's right here. Landed right here, Mr. Wizard.
Right there, huh?
Yeah.
So, did it describe an arc?
Yeah, instead of going straight up, like I thought, it went in a nice arc like that.
And by the way, this happens when you're riding in a car too, right?
It does?
When you throw a ball up inside a car, it's actually going on an arc
Oh, yeah.
because it has forward motion. So
Okay.
here, take your bike. Thanks very much for helping me.
Yeah.
And this time, as you throw the ball up on your way home, think about it from 2 points of view. One, you, the rider, and then somebody watching you. Okay? Okay, bye.
Bye.
You probably walk right past this common tree without realizing that it has existed virtually unchanged for millions of years. For a long time, botanists had identified it from fossilized remains and thought it was extinct. Then it was found in a remote area of China and brought to the Western world as a curiosity. The trees grew so well, even in smog-filled air, that they've become popular for planting along city streets. So next time you see a branch like this, take a closer look. Dinosaurs probably ate such leaves of the ginkgo tree. So, Laura, that was a container full of a gas.
Right.
These little white balls are supposed to be molecules, even though molecules are not white balls, right?
Right.
That they use them in textbooks too. They use little circles and so forth.
Yeah.
What I'm using them for here is to show what happens when you add heat to molecules. I'm now going to illustrate evaporation. Going to go from a liquid to a gas. You watch what happens. What happened?
Only some of the molecules get to the top.
Only got one up there, right?
Right.
What happened? Which one came up?
The hottest.
Right, the one that was moving the fastest.
Right.
So you get the idea. Heat is the motion of molecules. Now turn it up and get them all gone. This is like boiling, in which you're changing the molecules to steam very quickly. Now, however, I'm going to add one more important thing that happens when you try to boil something. Well, see what it says up there?
High pressure.
Yes. These are other molecules, red ones in this case.
Right.
Remember, molecules are not red balls either, right?
No.
What's going to happen when I put it down?
Well, these molecules will hit these ones and go back down,
Yeah.
so not too many will get to the
Right,
top.
there you get the idea exactly. Let's see. Okay. One, two, come on, two, three, okay. Now I'm going to leave the heat set at exactly the same temperature. In other
Right.
words, I didn't change that at all, but I am going to change from high pressure to
Low pressure.
low pressure. And what's the difference?
Well, this one has less red molecules, so
Yeah.
more of these will be able to get to the top.
All right. Okay. Remember, we didn't change the temperature, just turn it on. A lot more we were able to get through, right?
Right.
Now, what if you boiled it in a vacuum? What would you have to do?
You'd have to take away these molecules.
Right. Put those back down. And now,
Put that one back on.
you should have no problem at all, right? Go ahead, boil them away in a vacuum. Go! Brenna, how come you can see the plants outside the window?
Well, when you look out of the window, you can see what's outside.
Aha, what about at night?
Nighttime, it looks like a mirror for some reason.
Right, yeah. Well, the reason that a piece of glass works either as a transparent object or one that reflects, depending on which side it has the most light.
Yeah.
And that's the basis for my homemade copier. See, here's a piece of glass, right? See?
Yeah.
And I have it in two pieces of wood here so it can stand straight up.
Yeah.
And you are going to use it to make a copy of my grandmother's cat. The reason I call it that, she showed me how to do this when I was about your
Well,
age.
how can I copy the piece of glass?
Well, it depends on which side we have light on. And see here, I have a light over this. Now, look in the glass, and it's going to act what? As a mirror.
Yeah.
Okay. If you look through there, you can now draw on this side. Go ahead. I'll hold the paper for
You
you.
don't have to press any buttons.
No, just copy away. Ah, you forgot the eyes and nose.
Oops.
There you go. You now have an authentic original and copy made on my homemade copier. But how come you had it upside down?
I don't know.
Well, think about it. What happened when you look in the mirror?
It was upside down.
Yeah, so you copied it upside down. Okay, there you are. You see now why I say this is an inexpensive homemade glass pane copier. Danielle, you've heard the expression sunrise and sunset, of course.
Yes.
And I'd say incorrect.
Right. it's
Why?
incorrect. Because the sun's not really moving, it's the Earth that's revolving around the sun.
Yes. And you and I are going to not only prove that the Earth is moving, but actually time it. Here's how we'll do it. See, it's about noon. The sun is sort of directly overhead. And I've got it focused through this one eyeglass that has a piece of tape on the front, so we can get the image down here on this piece of paper. And I've got lines here, and these little lines here are each a half a degree. So get ready with start the stopwatch. And I'm going to move it so that that line is right there at the edge. Okay, go. Now, what I want you to do is calculate how fast the Earth is moving. First of all, can you figure out how many minutes there are in 24 hours?
That's 24 times 60.
Right, because that's the number of hours that it takes the Earth to make one revolution, right?
Right.
Okay.
So it's 24 times 60.
So I have the calculator here so you don't have to worry about it.
Okay. So it's
24
24 times 60
Equals.
equals 1,440.
And what does that answer mean now?
That means that's how many minutes there are.
For the Earth to make one
Right,
complete
right.
revolution. Now I want to know how long will it take to go through 1 degree? Do you know how many degrees it takes in a full circle?
360.
Okay, so how long will it take to go through 1 degree?
To find it out, you would divide 1,440 by 360.
Okay. There you go, 360. Okay, the calculator again. Just divide by 60.
60
360 equals?
4.
Okay. But you remember the marks that I had over the piece of paper were half a degree.
degree.
So how many minutes should it take to go through half a degree?
2.
All right, come on around over here. Well, you don't have to write it down. You know what 4 divided by 2 is, right?
Right.
Okay, very quietly now. It is 1 minute and 25 seconds. So in 35 seconds, that little black line should have crossed the whole thing. And doesn't it seem strange that here we are on the surface of the Earth, actually turning?
Moving, yes.
And you can see why ancient peoples had a hard time thinking that the Earth was revolving, and why we got that silly expression, sunrise and sunset. Okay, 145. 150. 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Did it go by 1/2 a degree?
Yes, it did.
Very good. Congratulations.
Thank you.
You figured out how fast the Earth is turning. See that electric tower up there, Giselle?
Yes,
Looks pretty tall.
very.
Okay, well, you're going to have to determine how high above us that is
How?
by using this very professional piece of scientific equipment.
It's just a metal piece and attached to a protractor.
Yes, with 2 holes here.
Yeah.
And notice, by the way, there's a thread going through 0 up here, and what is it down here?
0 degrees.
0 degrees, yeah, that's the vertical. So now, if you look through this hole and through that hole, and you get the top of that tower all lined up with it, you're going to obviously bend it down this way, right?
Yeah.
Then you can measure the angle.
Oh.
What the angle is from us all the way to the top of the tower.
Okay.
Okay, go ahead.
There.
Okay, what does it read?
24 degrees.
Okay, it's 24 degrees from here all the way to the top of that tower. Now notice there's one stake here
Yeah.
and another stake up there, 20 meters. So let's go do the same thing up there. Come on.
Okay.
Okay, Lizelle, you know what to do now.
Yeah.
Okay.
Just point it at the top.
Sight through the 2 holes to the top of the tower again.
There.
Okay, what does it read now?
27.
27. Okay, remember the first one was what?
24?
And 27. Okay.
Yeah.
Here, see, here are the 2 stakes. And each one of these squares is 10 meters, and the stakes were 20 meters apart, right?
Yeah.
The measurement from the first one was how many?
24.
Okay, take the pen and mark 24.
Okay, there.
Okay, now draw a line like that, all the way across. Okay. Now, the reading on the second one?
27.
27. Okay. Okay. Now you know how tall the tower is. If each one of these is 10 meters, how tall is the tower?
I get it where they meet.
Right, where they meet. So what is that?
10, 20, 30, 40, 50, and 60.
60. Okay, take a look. Do you think that's 60 meters up there? Think
Yeah.
about 20 meters, 40 meters, 60 meters, I think so?
60 meters.
Well, congratulations. You just figured out how tall the tower is.
Neat.
In dumps like this one are tons of potentially harmful waste products. The present methods of cleaning them up will take years. Dr. Ralph Poitier has what could be a better solution: microorganisms. In his laboratory at Louisiana State University are samples of the most dangerous and long-lasting of the industrial chemicals. The scientists have found certain strains of bacteria can digest them and turn them into harmless compounds. They're also testing similar techniques with microscopic plants called fungi. The lab-grown cultures would be released in the dumps to feed on the dangerous chemicals. So in the future, cleaning up hazardous dumps may be done more cheaply and quickly with waste-hungry microorganisms. I have 3 holes in this bottle, Aaron. One here covered with tape, another one here covered with tape, and one way up here at the neck covered with tape.
Okay.
You recognize it, right?
It's a pop bottle.
Pop bottle. What's going to happen when you take off the bottom tape?
The water will squirt out.
Okay, go ahead.
It's not coming out.
No, it started and then stopped.
Yeah.
See if I can give you a clue as to why it's not coming out. Take off the second one.
Okay. Oh, the air's coming in because it has to replace the water.
Right, so it's getting in right here. Now take the top one out. See, there's a difference in the two streams.
This one goes almost straight down, and this
Why?
one arcs out. I guess because there's more water on here, so it's being pushed out harder.
On this one down here, you mean?
Yeah.
There's the pressure, the water, the weight of the water. Well, all this water down here is pushing on that, while the weight of only this much water is pushing on that. Look, it's almost
That's right.
almost stopped because it's going to run
Yeah.
out of water. Okay, there's some more tapes over there in the windowsill.
Oh.
I want you to cover up all three holes again.
Okay.
Okay.
1, 2.
Wait, I'm going to take this top off first because we're going to fill the bottle with water again.
Is it down there?
Well, put it up to make sure you cover that hole real good.
Okay.
Because this time, by the way, you can do this at home if you want. You can get bottles like this quite often, don't you?
Yeah.
Well, you just take a hot nail and you can make the holes in it very easily. And you have tape around the house, I assume.
Yes.
You can cover it up. Okay, same idea, only this time the bottle is upside down. Now what will happen when you take that one off?
It'll just dribble over the rim.
Careful, careful.
Oh no, it'll come straight out because
Right.
all the water pressure is on this one tiny area.
Okay, take it off. What else do you have to do?
I have to take off this one.
Right. And the top one.
There we go.
Okay. Why isn't any water coming out of the top one?
Because
There's
it's letting
going
in
in.
oxygen.
Right. And now see the difference in the two streams?
This one arcs out farther while this one seems to
And why?
go down further because there is a lot more weight on this.
Right, a
than
lot
on
more
that.
weight of the water. So it's a sort of nice water pressure puzzle. And I assume you would be able to reproduce what we have done if you took this home. Here's the top.
Sure. Thanks.
Okay. And there you go. Take it home, try it on your
Thanks.
dad. Nick, here's a sort of quick little puzzle for you. I want you to tell me how much this ball weighs if I tell you that it weighs 200 grams plus 1/2 its total weight.
Okay, so you said it weighs 200 grams
Right.
plus half of that.
No,
Half of
plus
its
half of its
total
total weight.
weight.
Okay.
So 1/2 is 100 and the other half is 200. It has to weigh 400.
Now, take that again. How did you come out with 400?
Well, see, 1/2 is it's got to weigh half of the total weight plus half of the total weight. So if 1/2 is 200, we know that, then the other half has to be 200.
And you add the two together and you get
400.
400. Okay, you can check to see whether you're correct. You know how to use a scale like that?
Yeah, you move this around
Right.
to see if you're right.
If you move it up to 400, see if you're correct. Absolutely correct. Congratulations. Very smart gal. What's this? When you eat them, you don't notice that they look like many buds ready to burst into flower. But that's exactly what they are, buds on a plant that's harvested before they have a chance to mature into blossoms. So next time you get ready to cook them, take a closer look. You may see a bud partially opened to reveal the yellow flower of the broccoli plant. What's the temperature of freezing in Celsius? You know, Shane?
0 degrees Celsius.
Okay. Well, this is a very sensitive thermometer, and you can see the reading on there. What does it say?
5.9 degrees Celsius.
Yes, 5.9. It just changed to 6 there for a second. The reason I can say that is on the back, there's a little window over here where I can read the
see.
same thing you're reading in the front.
Okay.
And what we're reading is actually the temperature at the bottom of the glass because that's where the probe is.
Right.
So when you are holding a glass of ice water or soft drink or something, you know that at the bottom the temperature is 5.6, 5.7. Okay. Slowly raise the probe now.
The temperature's going down.
Yeah, 4.3, 3.6, 5.
3.5, 3.4.
Down just a little bit more into the... If we were actually freezing the ice, then it would be at 0. But right now we're sort of having the ice float around among water over there.
Right.
So it might not get right to 0. Notice, by the way, that it's colder at the top than it is at the bottom, right?
Uh-huh.
That's very, very important, because that means that because ice floats, the top of a pond gets cold and freezes, while the bottom can still be water at what temperature?
At 5.
4.5, 5 point something like that,
Yeah.
right? And that means the fish and plants can live underneath the ice, because there's air, there's air dissolved in the water, and it doesn't freeze.
I see.
Okay, so what is the temperature of boiling water in Celsius?
100 degrees Celsius.
Take the probe.
Okay.
Over here I have boiling water. You can check that.
95 degrees, 96 degrees.
96.2. Hey, it's going down. 95.
But how come it's not reaching up to 100 degrees Celsius?
Yes, how come? I thought you said it was 100 degrees. Yet we are proving without a doubt that it is only 95. 0.4, 0.5, 0.4. Think about this. When you boil water, you are adding energy from the stove
Right.
into the liquid, and you're changing it into a gas, and the gas is bubbling up. See all the bubbles?
Yeah.
And
Okay.
the molecules are flying off into the air. But air is pushing down on top of it. Right?
Okay. Yeah.
At normal atmospheric pressure, there's a lot of air pushing down on it. But if you take away some of those air molecules, then it doesn't take as much energy to make the water change from a liquid to a gas, right?
Right.
So
okay.
the temperature would
I see.
go lower.
Right.
In fact, when you get way up on top of a mountain, it would get much less than 100 degrees. As a matter of fact, you can use, what's the reading? 94.9, 94.8. You can use that to tell what the altitude is right here.
You can.
And that seems strange? Here.
Yeah.
Well, look. Here is 0 altitude and 100 degrees Celsius. That's at normal atmospheric pressure, in other words, the amount of air pushing down, at sea level.
Right.
Okay.
Okay.
Now, as you now go up in altitude, you're going to drop in temperature. And what's the temperature right now of the boiling water? 94.6, 0.7. Yeah, I'll call it 94 something. Go look at 94 and see what the altitude is.
It's about 1,000 meters.
About 1,000 meters or a little more. As a matter of
Yeah.
fact, what's the altitude here?
1,049 meters. So
you
it's
see,
pretty close.
you could tell, yeah, by the temperature of the boiling water, what the altitude is. You can see when you go way on top of a mountain where the air gets real thin, the temperature of boiling water might be way down at 90.
Yeah.
And people often say that you can't boil eggs very easily at the top of the mountain because the water isn't as hot. Now, you don't have a pressure cooker, I assume.
No, we
No,
don't.
most people don't have it anymore. Well, a pressure cooker is just the opposite of what we're doing. They now put a cover on it and make the pressure increase. So what's going to happen to the boiling temperature?
It's going to
Going
increase
to
as
go
well.
up, yeah, and that makes the food cook faster.
Oh, I see.
So next time someone says, what's the temperature of boiling water, what are you going to say?
100 degrees Celsius under normal atmospheric pressure at sea level.
Very good.